over his head.
Hello. Okay, welcome back, everyone. Please get seated, take a seat. And we're going to get started in just a second. Just a couple of housekeeping notes. So this is the last session for today. We'll be talking about aging and interventions. I'll be giving a talk of just a quick overview about the basics. Please don't knock over the camera. Okay, thank you. So I'll be giving a quick talk first, and then followed after me will be Danielle talking about metabolism, and then Kia Winslow will be talking about drug discovery, and then we'll be wrapping it up with the best, obviously, is Sergio with reprogramming. And of course, I'm wearing my Ocampo t-shirt 2016. Let me just double check that this is working. Yeah, okay, we're good. Okay, we're good. Okay, great. And then tomorrow we also have another session, day of sessions. So definitely join us for that one too. Okay, cool. So let's continue. Just a bit about myself. I'm the co-founder of the Longevity Biotech Fellowship. My name's Nathan. Running this course with Cat and also Mark Hamalainen, my co-founder. And the Longevity Biotech Fellowship is a nonprofit dedicated to helping people make career transitions to work on longevity. And I'm also involved in a bunch of other projects, but we don't have time for that. We only have 15 minutes. So I'm going to be talking about how to modulate aging. Just a really high-level overview. So just 4 points in my talk. I'm going to be talking about just a little bit about the history and strategies behind modulating aging, then some frameworks for target selection, and then talk about just some of the modalities that are involved in biotech in general, which we apply as well to try and extend lifespan in humans, and then some quick words about testing these modalities in humans. Cool. Okay, so history. So I think the first instance of actually modulating aging in an organism, like intentionally, was back in the 1930s, 1934. Clive Mackay did a calorie restriction experiment in rats. So calorie restriction, just restricting the amount of calories, the amount of food that these rats were given. And the rats that were fed less actually lived longer than the control rats that were just normally fed that ate ad libitum. And they showed about a 30% increase in lifespan in rats by restricting the amount of food that they consumed. And fast forward many, many decades, another sort of inflection point in terms of interventions for aging was this paper in 2009 by Rich Miller and Harrison. Basically, this was the start of the ITP program, where they found that rapamycin, a drug that is usually used for kidney transplant patients, it's an immunosuppressant, this interesting drug, which happens to inhibit the mTOR pathway, actually extends lifespan in mice, about 14% in female mice and 9% in male mice. So this was sort of the first demonstration of lifespan extension in mammals, in mice, with just like a single molecule, a single small molecule drug. And this was, quite unexpected. Okay, and then, so fast forward to today, the National Institutes of Aging does a program called the ITP, Interventions Testing Program, where they will try different molecules and compounds to see if they extend lifespan in a 4-way cross of species of mice. So this is considered the gold standard for testing compounds in mice to see if they extend lifespan. It's done in 3 different labs in the US. So and there's about 7-ish compounds that have been shown to extend lifespan in mice. And some of them work in females, but not males, and vice versa. Okay, cool. And there's more interventions. If you're interested, you can check out Laura Deming's Longevity FAQ, where she kind of lists a list of 95 things that make mice live longer. And if you're also interested, you can check out the drug age database by João de Magalhães at University of Liverpool, I believe now. This is just a database of studies of compounds that have been shown to extend lifespan in mice. So there's quite a few, but let's talk about just strategies now. So from a very high level, if you want to do something about aging, you can either try and slow it down or you could try and reverse it, right? So those are the kind of two strategies that you can employ. You could try doing both at the same time. And so slowing aging, that really usually is restrained to decreasing damage accumulation. So examples of that is you could try and improve your the function of your DNA damage repair, right? You might not be able to completely stop DNA damage from occurring, but you could lessen it. So then you would accumulate fewer mutations, and then maybe that's a way to slow down an aging mechanism and therefore extend lifespan. You could also perturb various metabolic pathways to try and slow aging as well. Maybe slowing down like cell growth cycle. So that's basically how rapamycin works, by inhibiting mTOR. And then you can also try doing age reversal, right? Rejuvenation. So this would be trying to reverse aging, potentially in like phenotypical measures of aging or reverse decline in function. The big issue here is when you're talking about reversing aging, what do you actually mean by that? Because we don't have like a quantitative definition of aging. People have these just sort of like ideas of what they mean when they say aging. And you can try to reverse aging maybe on a local level, like in a specific organ or tissue. Like for instance, David Sinclair has a company that's working on reprogramming specifically in the eye, right? Or you could try doing something more systemic. And then there's different ways to try and measure aging. You could try measuring with molecular measures. So obviously DNA methylation is extremely in vogue right now in terms of being used for biological age clocks. But there's still a lot of research that needs to be done there. And then you could try looking at phenotypic measures of aging, and also you could measure function. So examples, as I said before, you could do something like partial reprogramming. Many companies are doing that, trying to reverse the epigenetic profile of the cells in your body. So that's making your cells look essentially younger from an epigenetic perspective. But then you can also try things like just full out replacement. So you could, if your cells are old in a particular tissue, you could just replace them with young cells from either like a donor or from induced pluripotent stem cells from your own autologous cell therapy. Okay, so let's continue. So frameworks for target selection. So let's say you want to either slow down aging or you want to reverse it, but then how do you actually figure out what the thing is that you want to modulate at like the cellular level? So there's different frameworks. People have really already mentioned some of these sort of fundamental frameworks of aging biology in previous lessons of this course. So the most famous of which is probably the hallmarks of aging right now, which there are 12, and potentially expanding universe of aging hallmarks. And yeah, there's the typical culprits, telomeres, mitochondria, et cetera. So scientists have found potential mechanisms of aging by looking at model organisms and how these sort of molecular targets change with age. And as they perturb them in model organisms, they can see increases in lifespan or decreases depending on the way that you change them. So then they collate all these mechanisms and call them hallmarks of aging. Okay, great. And predating the hallmarks of aging was the SENS categories, SENS Research Foundation, of course, looking at very similar types of mechanisms. There's a lot of overlap between the two, but mostly SENS is looking at it through the lens of damage repair. Okay, there we go. So those are two ways to look at it. You could pick a target, right? A molecular mechanism of aging, and then try and drug that target or modulate it with some sort of compound or whatever biotech modality. But there's other things you could do, right? So if you don't really know the molecular mechanism of aging, you could just try and replace the tissue, right? So people are doing that with cell and tissue and organ transplant therapies. And then you can also do something like a hypothesis 3 approach. So you could do a high throughput screening. Basically, you just throw a bunch of drugs at either some cells or some worms and see if the worms live longer or if the cells exhibit some sort of more youthful phenotype. And then in that way, you could just try and come up with the drug without even knowing the mechanism of aging that you are targeting. But generally speaking, you might want to find the target after the fact, and you can do that with other sort of techniques in biophysics, etc. And and another thing is you could try doing some big data analysis. So if you have like a large omics data set, maybe you can find some genes, etc., from that to target, or proteomics, whatever, and try and modulate that. Okay, cool. So how am I doing for time? Okay, great. So let's just go quickly through some of the modalities that are used in biotech. So from the FDA perspective, drugs are kind of split up into just like typical normal drugs, small molecule drugs, and then biologics. Biologics are basically therapies that are derived from living organisms or cells. And so there's a bunch of them. In the biologics section, there's like peptides, which are just like short chains of amino acids. If you have longer chains of amino acids, you get proteins. Monoclonal antibodies are a type of protein, but used mostly in like immunotherapy and such. Then you have things like gene therapy, other nucleic acids like mRNA, et cetera, cell therapy, and then, you could do like tissue engineering and other organ replacement sort of strategies. So this is from my newsletter from a really long time ago. I highly recommend, if you've never done this exercise before and you want to learn more about biotech, you should just create a cheat sheet of your own for like all the different biotech modalities, how they work, what they're good for, some examples, et cetera, et cetera. So that's just there if you want to try that yourself. But let's just go quickly through not all of the biotech modalities, but just like a couple of the more popular ones, I would say. So small molecules, that means small chemical compounds, usually a molecular weight of less than 1,000 daltons or 1 kilodalton. A dalton is basically the molecular weight of a hydrogen atom. And basically the way that small molecules work is they bind to specific proteins or enzymes or cell receptors to modulate their function. Small molecules are good in the sense that they typically have broad distribution, so they can get everywhere in the body. That can be a good thing or a bad thing, depending on what you want. They can enter the cell pretty easily because they're small. They can cross membranes. But the problem is, because they can get everywhere and they're not too specific in what they bind to, you can get a lot of off-target effects or side effects, right, from these sort of things. But examples, like aspirin is a small molecule drug. Rapamycin is still technically a small molecule drug, although it's quite large. That's rapamycin. And companies like early senolytic therapy companies like Unity Biotechnology, they mostly develop small molecule drugs to target certain anti-apoptotic pathways to kill, essentially, senescent cells. Okay, cool. Moving right along. So monoclonal antibodies, also a pretty well-used biotech modality. These are large Y-shaped proteins that bind specifically to either like antigens, specific compounds, or like cell surface receptors to affect activity of the cell, or recruit the immune system to do something to the target. Monoclonal antibodies are used a lot in cancer immunotherapy. But some examples that you might have heard of, so Humira is used in many different cases, but Aduhelm, the Alzheimer's drug from Biogen, is also a monoclonal antibody. In the aging space, there's not that many companies developing monoclonal antibodies, but Arda Therapeutics is one company that is basically trying to use immunotherapy to remove pathogenic cells. So that could be senescent cells or pro-fibrotic cells. Moving right along. We have gene therapy. So gene therapy basically means either the insertion, editing, or deletion of genes in cells in your body. And by doing this, you can either confer like new function, or you can correct pathogenic genes, SNPs or whatever. And then you have the problem with gene therapy is it's really hard to deliver these genes to the entire body. And there's all sorts of issues with the actual gene delivery process. Mostly what's being used now are AAVs, or adeno-associated viruses. And so examples of some gene therapies, there's not that many gene therapies approved by the FDA right now yet. It's still kind of like an emerging class of therapies, but Luxturna, that's to correct like a rare disease of blindness. And Oishin Biotechnologies in the longevity space is developing a P16 suicide gene to kill senescent cells. And then Minicircle, who's here, they gave a presentation earlier, developing gene therapy for delivery of follistatin. Okay, and then cell therapy. So you can also deliver cells therapeutically. So cells can do all sorts of things, and you can consider them as some sort of living medicine, and they can secrete different things. Cells can be used in sort of immunotherapy, like and certain immune cells can be used for cancer. It's like in the case of like CAR T. You could also use cells to replace old or dysfunctional cells. So there's a company called Lineage Cell Therapeutics, which is trying to treat age-related macular degeneration by replacing a certain retinal pigment epithelial cell in the back of the eye. And then there's a company called Blue Rock, which is trying to transplant dopaminergic neurons derived from iPSCs, or induced pluripotent stem cells, from your own body, and to treat essentially Parkinson's disease. So there's all sorts of different ways that you can leverage cell therapy. From a high level, most of the drugs that are approved in any given year are usually small molecule drugs. Most of biotech companies work on small molecule drugs. There's a question of whether just by using small molecules will we get large effect size in lifespan in humans if we develop these therapies. But potentially there's ways to combine therapies together to get additive effects. So that's also something that's being tried in mice, but potentially that could be extended to humans in the future. And yeah, I think I'm just going to end it there because I feel like we don't have enough time to talk about how we test these in humans. But if you're interested in that, you can find me later. Okay, cool. Okay, so I'm done. Thanks.
Life is action, not contemplation. Life is action. So while it's very valuable to talk about the concepts and the theories around longevity, it's also very valuable to look at what we can do today. I'm Danielle Ruiz, and I'm CEO, founder, and medical provider at Everest Health Partners. We're a medical clinic that's partnered with the Methuselah Foundation, and we've developed the Methuselah Protocol based on many years of research, the abundance of research that's out there around the health span and health interventions, measures of health, age, and mortality risk. We have built this protocol for individualized application to every person to help improve their health long term. So today we're going to be focusing on metabolic health. We'll be reviewing the different forms of metabolism and then what we can do about them.
Great.
So as we age, of course, like everything else, our metabolic processes change. Our metabolism is like the symphony orchestra in that we have different instruments, different notes. They all do different things. They're all very useful, and they combine to create a harmonic song. But as we age, we've got that orchestra playing for 80 years. Eventually, you're going to have a string that pops, your piano's going to get out of tune, and it results in chaos. That song no longer is beautiful. For example, I have many patients that come to me when that state of chaos where they're beginning to see the changes with their health. They're beginning to feel the issues of aging. One patient recently had a stroke and came to me already having that cardiovascular damage. She had wildly uncontrolled diabetes, wildly uncontrolled hypertension. And one of the biggest problems with that slow progression of age-related diseases is that the body stops communicating with itself. So you can't really feel at that point the danger that's coming. She would end up going to the hospital about every 2 weeks because she couldn't feel when that danger was coming. Thankfully, it's not too late until it's too late, and there's always things we can do to get our health back on track. So we're focusing on the different systems of aging. As we age, our metabolism changes. What is metabolism? Metabolism are many different systems in our body that result in energy, the production, the processing, and the utilization of energy in our body. As we age, that energy production goes down at a cellular level, but also our ability to use it changes. Our nutrient sensing changes. We're no longer able to absorb proteins, the building blocks that we need, as well as micronutrients and vitamins as well as we get older. That cliff depends on the individual, but usually comes about age 60 or 70, so that changes. And also internally, we need more antioxidants. We need more vitamins to offset that damage that we've been experiencing our whole life to stay on track. And we're not able to sense those nutrients, transport them into the cell and use them as well. Hormone regulation, we all know for women, changes pretty significantly, but that's just one part of the picture, reproductive hormones. There's also hormones that control our sleep, that control our blood pressure, very complicated systems, and they're very important. And of course, cellular stress and senescent cells. That damage accumulates, our cells are no longer as effective, we're no longer able to repair as well, and eventually we get a buildup of inflammation and dysregulated processes that result in disease.
Really what I think about, but
there's 4 main ways that we obtain these building blocks to produce energy and function in the body. The first one we'll talk about is carbohydrate metabolism. Carbohydrate metabolism is our body's favorite way to get quick and efficient energy into the cell to create these processes. Our brain especially loves carbohydrate metabolism because it's fast. It allows us to operate quickly and efficiently and cleanly. The issue that comes from carbohydrates is not carbohydrates themselves, it's the metabolism. Is that going to result in inflammation, or is that going to result in nice, clean energy? Lipid metabolism. We can think of lipids as like a construction truck. Lipids allow you to gain access into the cell. They transport things to and from the cell. They also contain building blocks for things like our skin, our cell walls, our nerve sheaths, all very important aspects. And they also produce energy. Triglycerides are a great source of energy into the cell. So if you don't have enough lipids, you'll start to see things like skin dryness, right? Our skin barrier at a basic level starts failing. Proteins are like the Legos of the body. They're great building blocks. They build our tissues. They build our enzymes, the most basic functions telling our body what it's supposed to do. Many hormones are also built from proteins, things like insulin and human growth hormone. And they're really essential for our immune system because our antibodies are proteins. And finally, nucleic acid metabolism. So nucleic acid, our body has 2 options here. It can create this puzzle that then fits into different areas in the body. Either internally, within the cell, it can combine nutrients that we obtain from diet to produce these nucleotides, or you can obtain nucleotides from the diet through things like yeast and fermented foods, mushrooms, and meats. And these really are very important building blocks for things like DNA repair and gene expression, and also our immune system. These are involved in B and T cell immunity. So now we have the basics. Just a reminder, life is action. So what are we going to do about this? Knowing the background of our metabolism is an important place to start so that we can figure out these interventions to result in a long and healthy life. The biggest thing is lifestyle. This is something that most people take on themselves, but it really is highly individual and it's very complicated. There's so much information out there, information that is true and science-based, but maybe not applicable to you as an individual. And there's also a lot of snake oil, clickbait out there that's really confusing the average person and even the intelligent person. that's very, very well educated around health and longevity. We have basic things that we can do for our lifestyle, things like our nutrition, getting those building blocks for our metabolic processes, and also things like our eating style. They touched on calorie restriction. Ketosis is another method of potentially improving health span. Fasting kind of combines the two, but of course this is highly individual. Nothing is going to be right for absolutely everyone, which is where it's important to work with a specialist who knows how to interpret the data, the body of data, and then apply it to you as an individual, not just as an individual today, but our health is changing every day. Recovery is also important, not just quality sleep, but letting your body recover and repair from the stresses of good things like exercise. So you're going to choose one lifestyle intervention that's probably going to be the biggest bang for effort. It would be whether or not you exercise regularly. And there's many forms of exercise that result in better health. Probably the biggest targets would be aerobic exercise, strength resistance training, and high-intensity interval training. But there's lots of other ones to choose from too. And of course, we're also trying to avoid damage. Now, stress can be beneficial. It tells our body that it needs to repair, it needs to improve, it needs to get stronger, it needs to get more resilient. But you don't want to have so much damage that then your body can't actually recover and you begin to fail. So we want to reduce things like emotional stress affects us negatively. Of course, things like toxins, cigarette smoking, excessive alcohol use would not be beneficial either. There's lots of medications. I use that just as an umbrella term. Of course, you could also say that food is a medication, and that would be true. But we're talking about things that you extract and concentrate and put in your body, like vitamins, herbs, supplements, nootropics, the whole list. And this is also highly variable for each individual. This pertains to both lifespan and health span, but it's also very symptom driven. So for example, I had a patient who came to me, and the biggest barrier to him choosing to do those lifestyle changes, for so difficult for him to overcome those behavior changes, had to do with anxiety. So he couldn't sleep well as a result of his anxiety. He couldn't absorb nutrients, couldn't have good digestion because of his anxiety. He couldn't engage socially. He couldn't exercise. And so addressing those things helps you overcome those barriers, and also specifically can address these processes that add up to the syndrome of aging, the bundle of issues that comes with aging. For example, prescription medications. Of course, if you have an active disease, we need to survive today to survive tomorrow. We need to overcome that actual disease and to be able to get back to a place of health. And also things like senolytics, metformin can be appropriate for certain people to get to a higher level of health. There's lots of interventions also that are not under those couple of umbrellas. One that I really would love to mention is hyperbaric oxygen therapy, which is a treatment where you are exposed to a very oxygen-rich environment, and then you are in a very high-pressure environment to a specific dose. And what that does when you're in that high oxygen, high pressure environment, it pushes the oxygen into your tissues, into your cells. It increases cellular respiration. It increases ATP energy production in the cell. It boosts healing. It boosts the effectiveness of antioxidants. It's really incredible for reducing inflammation and boosting healing. There's other things that it can help with as well, but those are the two main targets. One thing that I do hear kind of often as a concern with HBOT is the potential for reactive oxidative species, right? Because oxygen is a toxin. But the positive thing is we're working with time and dose, right? So we're working up to the point where we're getting the most benefit without problems. Safety first.
Oops.
And what can you do with all this information? Well, I would urge you to make it personal. Everybody's health is important. Every human is valuable. So I would focus on your own health, your own reasons for living longer, living healthier, and your family's purpose as well, your family living well and connecting with them long-term, staying purposeful, staying healthy, staying happy, and working with a specialist, someone who is experienced and capable of helping you find these interventions and these measures that will be effective and safe for you personally. There's other ways also in this industry, supporting research, publicizing that is an option. Many people have no hope when it comes to age. They think they're fated to get ill, and then we make poor choices that result in that earlier aging process. And also improving access. So we want everybody in the world to be able to have this as an option. That could look like things like using potentially AI or digital twins to boost the knowledge, boost learning process, reduce cost, and improve access, no matter where you're located or what age you are, your technology use. So just remember that life is action. Let's stay active. Let's stay alive. Thank you.
But it's special one.